So, without no further ado, I'm going to hand you over to Eugene, who from NVIDIA, sorry. He's going to talk about an approximate Mie scattering function for fog and cloud rendering. So, thank you very much.
All right, thanks everyone for coming. First thing in the morning, appreciate it. Let's see how this goes. All right, so I want to talk today about how light interacts with water droplets. So depending on the scale of that material in the scene, like this fountain, we're just going to have to model those drops and trace rays through them. But the same sort of structure at a different scale relative to a pixel, we might use a participating media to describe how light is going to interact with droplets. And especially when the droplets get very small and create clouds and fog, important and challenging atmospheric effects that we need to get right. And it's well known, and it's been presented here many times, that sort of the isotropic and Henny-Greenstein functions in our renders that we reach for don't do a really faithful job at getting the appearance of light scattering and things like clouds, because the interaction with particles generates this very complicated shape that Mie scattering theory gives us. And so we can reach for free off-the-shelf tools, plug in parameters, and compute these interesting looking shapes. But if we want to evaluate and sample these in our renderer, we end up with these large tables and a whole bunch of annoying numbers that depend on wavelength and the particle size. And so this isn't ideal. And so what I want to present today is a new phase function that can approximate fog and cloud scattering, pretty faithfully match the appearance of a tabulated approach. It has a single parametric parameter, just the size of the droplet, and it's fully analytic to evaluate and sample, so we don't need these tables and pre-computation. And so I'll start by reviewing some properties of Mie scattering before proposing the model and deriving the sampling for it before we look at some results. So let's start with Mie scattering theory. So this describes the phase function when the wave properties of light consider how they move through a droplet. And it creates these complicated functions that change depending on the size of the droplet relative to the wavelength. And depending on the application, we'd like to have a good way to describe these different phase functions. And they have some common properties, like a strong forward peak. And this is a log-based plot, so most of the energy, like 95%, is in the forward half. And there's some interesting structures in that other 5% that lead to interesting effects. And we'd like to try to capture most of these analytically for some applications. And if we consider the spectrum of particle diameters that we might want to consider in various applications, on one scale, the tiny particles lead to Rayleigh scattering. There's a nice simple analytic function for that, and that's no problem. And I want to briefly look at the other side, where you let the droplet diameter go to infinity, and the wave nature of light will diminish and drop out. So you won't have that forward peak anymore, but you still have this rather interesting function. And it turns out you can work this out analytically using a very similar process that Marshner and colleagues used to derive hair scattering functions. So if you imagine a ray of light reaching the droplet with some offset h from its circumference, you can imagine the Fresnel equations and Snell's laws giving you the various paths that move through the droplet. And you can index those over the order of transmission events that happen. So you get the familiar R, TT, and TRT interactions. This sounds a lot like hair scattering math. And indeed, 20 years ago, Marshner and colleagues used the same equation that describes the various angles that happen within this one-dimensional analysis, two-dimensional analysis for rendering scattering from a cylinder. And you just have to use a slightly different distribution of H when you consider a spherical droplet. And so you can actually work these out for the first couple bounces. So the R scattering lobe is just a uniform set of disk of rays hitting a sphere, which will reflect isotropically. And so the only thing to add to that then is just the Fresnel term evaluated at the half angle times an isotropic function. And that'll create this red curve here that's sort of the main body of the interaction. We can use derivations that I can find in hair scattering papers, and I suspect these must exist somewhere earlier in other literature that has studied rainbows and so on. If you know where these equations have appeared before, please let me know. You can crank these out and get an analytic function for the TT interaction, and that's this blue curve. And putting these together, That pretty accurately describes the bulk 95% of the forward energy of the interaction. And so what is left, indeed, if you're predicting this from your knowledge of hair scattering, is indeed the TRT is creating the major spike on the back, and then TRT. And with these first four interactions, you're describing most of the scattering of a very large droplet. But getting your hands on analytic functions for these last two lobes isn't really practical. The equations are quite overwhelming. But it's sort of interesting to think of the relationship between the caustics in the TRT lobe that we're familiar with giving those glints in a fiber as actually being the exact sort of same things that give us rainbows for droplets in the atmosphere. And it's not really clear when we come back to the picture where we want to render 10 micron diameter droplets that knowing these analytic endpoints is really going to help us. It's clearly showing us why we've got some spikes and interesting features in the back end of the phase function, but we're going to have to do something different if we're going to have to describe all of these. So what we proposed to do was to try to simplify things to make it a little practical. Clearly, an analytic approach isn't going to describe all these shapes perfectly. So we first averaged the distributions uniformly over wavelength, and also consider just a log normal variation in the particle size, because not every droplet in the cloud is going to be the same size. And then we'll just fit the strongest components of what's left with some analytic functions and see how close we can get. And hopefully this will work because that 95% of forward energy is the smoothest component. So if you just take a single wavelength and a single diameter, you get this really complicated shape. Average this over the visible spectrum uniformly, and a lot of that variation goes away. And as I average over a distribution of particles between these two, it softens even a bit. So you've still got some spikes on the back, but that core 95% forward energy is now pretty smooth. So let's try to approximate first this forward peak. It's well known that for a single diameter and wavelength, the forward diffraction peak is asymptotically von Mises-Fisher, so it's an exponential function. But we found after we averaged over droplet size, Henny-Greenstein was a better fit for that. And so we proposed to just blend a Henny-Greenstein lobe for the forward peak with some other analytic function for everything else. And we looked at 5 known phase functions that are analytic to evaluate. And we found that this one from Drain in 2003 for scattering from interstellar dust by far did the best. And this is nothing more than a Henny-Greenstein with its G parameter multiplied, which is kind of strange, with a generalized Rayleigh distribution where there's an extra alpha parameter to scale that quadratic cosine. And then this function just normalizes this to be a proper distribution. And this phase function is very nice because it specializes to 3 important cases. You can recover Rayleigh scattering, Henny-Greenstein, and Cornett-Shanks, which has sometimes been used for sky scattering models. And so we propose then for rendering fog and clouds, we'll have some weight that will mix the drain function for the bulk of the scattering together with a Henny-Greenstein lobe for the forward peak, and then we'll have 2 parameters for the shape of that drain function. So all up, we need to solve for 4 numbers for every diameter of droplet, and let's see how close we can get. So we started with something that works well for fog and clouds, around 10 micron, and simple RMS log space fitting gave us something like this. And it's doing a pretty good job here for that 95% of the energy. And it's nice that without a third lobe, it's putting some energy, sort of the average behavior in the back half of the model. And so just naively dropping this in a render and comparing to sort of a tabulated me render, if I flip back and forth here, you can see that the core quality of the character of the cloud is proper. It seems well approximated, but there's an intensity change that is definitely undesirable. So going back to the drawing board a little bit, we adjusted the loss function when we solve for these 4 parameters to still use RMS error in log space, otherwise the forward peak would dominate everything. The sign term is just because we're integrating uniformly over a sphere, but we introduced this extra absolute mean cosine in the loss function. And this accentuates the importance of the forward and backward ends of the function, and also makes sure that the mean cosine of the approximation is very similar to the target. And after we did this, we've captured on the right with a fully analytic phase function the bulk appearance of a tabulated approach without that intensity change. And so this was just one element of the span of particle sizes that we'd like to model. So we went and solved the 4 parameters over a wide range of diameters, and we broke this down into 4 sub-ranges just to keep the mapping equations simpler so they don't get too complicated. And as we did this, we noticed that the errors of our model to the target as compared to like a double or triple Henry-Greenstein approximation were about 1/3. It was really doing much better across the board. And when I plot errors for the various particle sizes, I'm going to switch from this sort of polar plot to just mapping one side of the symmetric function from 0 to 180 degrees. So you'll see the forward peak on the left and that forward energy matching well, and then a bit of error in that log-based 5% of energy on the right. And so for large diameters, fairly simple exponential functions will give the 4 parameters that modulate the drain and Henry-Greenstein lobes. And the peak and the bulk first sort of 80 degrees of energy is being really tightly fit by these functions, which is working nicely. As we reduce the particle size, this trend pretty much continues. It's around the 0.2 or 0.5 micron area where we saw the largest deviation from the target. But overall, it's still probably usable. And then in the limit of tiny droplets, because the model can produce Rayleigh scattering exactly, the error goes back to 0 as you move d to 0 with fairly simple fitting functions. And so now how are we going to sample this thing? It is published in multiple papers that there is no CDF inversion for drain or Cornet-Shanks, and we found that actually not to be the case. Relying on Mathematica, working out the CDF as usual is no problem, and noticing that this square root term is the same, doing just a simple substitution, introducing a new variable v for that, and giving that to Mathematica after substitution, it quickly finds that you can do CDF inversion for the cosine by solving a quartic equation. It's quite happy to give you pages of math for those solutions. You find the one that doesn't produce complex numbers, and simplify common expressions. And we got it down to basically 10 lines of code that with a single random variable xi will give you the cos theta equal to u that you need to sample that, and then you just do your normal azimuthal sampling and the rest of the lobe. And we provide validated code so you don't have to type these ugly equations in at home. And so given that, and given that Cornet-Shanks is a special case, to the best of our knowledge, we've now given the first analytic sampling for all 5 of these functions. So let's, in the remaining time, look at some results. So I've shown these images several times already. Let's just zoom in and compare these. So often we tend to just have a single G parameter in many scenes that we render. It's tempting to just use the mean cosine of about 0.85 and render a cloud, and it looks pretty nice. Using 2 Henry-Greensteins, you can get sort of a closer darkened energy, but it still doesn't have quite the right quality as I flip here to the reference. So let's go back and forth a few times between the double Henry-Greenstein and the tabulated approach. And notice sort of that crunchy detail in the actual MEF scattering that you just don't get with the sort of soft, fuzzy Henry-Greenstein. And now if I flip back and forth between this target function and our drain Henry-Greenstein approximation on this projector, you may not even be able to see the difference. And despite the fact that we haven't got the back 5% perfectly accurate, we found that this actually is doing a pretty surprisingly good job in a lot of cases. And so rendering uniform fog in realistic scenes, note here as I go from a single Henry-Greenstein to our approximated functions, look at how the light scatters around those bright street lights. It has a nice sort of natural glow. And I find that when I look at the overpass and sort of the gray hazing in the scene looks rather CG and flat here, whereas this makes me want to grab my raincoat. I feel like it's going to be really wet outside. And so playing with this, we didn't expect such analytic functions to work so well, and they're working pretty great. If you put a light source above a bank of fog and look at it from below, you can actually sort of see the whole phase function present itself. And notice that these peaks in the back half of the energy show up as these slices that the Henry-Greenstein lobe on the left isn't producing. Comparing, again, a couple different sort of uniform fog examples, you'll find like the balance of energy in the single and double scattering in the fog just is a bit out of balance with Henny Greenstein. It's a bit more broad and diffuse, whereas you get a little more variation in the proper me scattering, and we more closely approximate me with our approximation here. The general trend continues, though, and of course this method has its limitations, as you're all waiting to see. As you pull the camera back next to the light source and look down, you're going to see single scattering that has elements of this back peak, which we haven't perfectly approximated. And so in the cases that you do need that fog bow and that backward spike, you're probably going to need a tabulated approach or something else. But to conclude, it seems like this drain function is really quite good now that it has sampling. It can get you 4 useful phase functions as well as the model that we've presented for fog and clouds. We've provided the analytic sampling code for it. Give it a try and hopefully it'll work for you. I want to thank Andrea and Steve for helpful discussions, and thank you for listening.
Thank you very much. Do we have any questions at all? Can't see people coming. I'll think of a question. I just wondered if you, just curious about benchmarking in terms of the computation for this method and previous methods, whether in terms of the sort of the processing time, if there's any sort of main differences. I mean, the results are pretty visually very appealing. But.
Yeah, the only testing I've done so far was just within the Omniverse renderer that we've been developing at NVIDIA. And with all the other costs of intersecting with geometry in the scene and so on, all these results were rendered in there. And I maybe saw a 5 to 10% slowdown compared to, say, a single or double Henny Greenstein.
Oh,
something
cool.
like that.
Thank you.
Yeah, great work, Eugene. I love it. So this is all a two-dimensional analysis for your functions, is that right? So that works for a hair, which is basically a cylinder, but we're talking about spherical droplets. What?
Yeah, so there's a symmetry if you just assume a uniform disk of rays arriving at a sphere and scattering out. And so when I've done two-dimensional plots, really these are symmetric functions that would describe uniform cones of different directions. So
right.
For a given angle theta, you have the same intensity in all of those cones. And the relationship I was making to hair scattering models ultimately wasn't used in the approximations that we did. But there is sort of that interesting connection that you can analyze what's going on in both the cylinder and the sphere by just projecting down a set of paths into a disk, a two-dimensional problem. But we are fully describing a three-dimensional droplet.
Yeah, got it. Yeah.
Cool. Anybody else? No? All right. Well, thank you very much indeed. Thank you.